So let's start. Hello, everyone. So we are from CERN. We're here to talk about our network evolution at CERN. My name is Belmiro. I work in the cloud team.
My name is Ricardo. I also work in the CERN cloud team.
OK, so we're going to start with a very little introduction about CERN for you to know what it is, and then we go through the evolution of the cloud. So CERN is the European Organization for Nuclear Research. It was created in the 50s. And what we do there is basically fundamental research. It was created to answer very difficult questions. So like these ones that you are seeing on the screen. So what is the universe made of? What is the state of matter just after the Big Bang? These kind of difficult questions. And to answer all of this, we have a lot of experiments. And one of the most known experiments is the LHC project. So what we are seeing in this picture is the Large Hadron Collider. It's the biggest particle accelerator in the world. Basically, it's a ring with 27 kilometers that is in a tunnel, 100 meters underground. You see these blue pipes there? These are superconducting magnets that, to work, they need to be cooled down to around 1 Kelvin. This is around minus 271 degrees Celsius. So very, very low temperatures. It's even lower than the outer space. And inside these pipes, they are smaller pipes where the beam of particles travel very close to the speed of light, and they collide in these huge machines. These are detectors. And basically, a detector is a photographic machine. So it takes a lot of pictures, 40 million pictures per second. This produces up to 1 petabyte of raw data per second. Of course, we don't have capacity to store all of this. So these detectors have filter systems that filter all the data, searching for only the interesting events. And we only store those. And doing this, we reduce the data to a few gigabytes per second that we store in our data centers. All that data needs to be analyzed. And most of them is analyzed in our data centers in a cloud powered by Openstack. So in this slide, you can see the size of our cloud. This is from one of our monitoring dashboards. You can see that we have more than 300K cores, more than 9,000 hypervisors, more than 4,000 projects, a lot of users. This is the current size. OK, so in our clouds, it's in production since 2013. We decided to use cells from the beginning. Why? There are a lot of advantages. If you are using cell, one of the main advantages is that basically you are sharding the RabbitMQ and the database. So this allows you to scale your infrastructure without overloading these components. So it's great for scalability and flexibility. If one of the cells is down, your cloud is not compromised. So all the other users that are not using that cell, they will not notice. Also, we can basically partition the infrastructure, considering the capabilities that we want to offer to the users. So we have cells with different configurations, cells where we do CPU pinning, huge pages, cells where we only do GPUs. So you see that is a very flexible architecture. This also is helping us with the Nova network to Neutron transition. Initially, everything was Nova network. And now, when we do the migration, we do it cell by cell. So we see the flexibility of cells. Yesterday, I gave a talk about the cell architecture at CERN, the upgrade from cells V1 to cells V2. The video, I think, is already available. So each cell has its own control plane. we only have a control plane per cell, and then we have the hypervisors. A configuration that we like to have is around 200 hypervisors per cell. Currently, we have a total of 70 cells. And the number of VMs that run per hypervisor, that changes a lot considering the use case. We have the batch, the data processing use case, where we have large VMs. So those hypervisors usually have only 4 VMs. And then we have the services that we also run, all the CERN internal services that we run at CERN. And that is a more, that is a different use case or a different architecture. So we can have up to 30 VMs per hypervisor. So now going into the network that we have at CERN, the architecture, it was designed a long, long time ago, more than 10 years. It's a flat architecture, but segmented with multiple broadcast domain to be scalable and to give also some protection to the network itself. These are terms that we use there. So we have the primary services, that is the network where the hypervisors are. And then we have the secondary services where the VMs are. Each primary can have multiple secondaries, and each secondary is attached to a primary service. So when we create VMs, we need to create them. When we give an IP to a VM, we need to make sure that it's running the right primary. We, like most of deployments, have a network database. Basically, it's the source of truth of everything. It was already there before we deployed the OpenStack. And basically, it contains the information of all the devices, all the interfaces, all the networks that we have there. Not only that, but also alias information, and a lot of stuff. And it's also used to configure routing, switches, the firewalls, everything. That is the source of truth. Everything, all the scripts that the network team uses go through the LANDB. So one of the challenges was we already have this network database. Now we are deploying OpenStack, so we need to continue to support this network database. So initially, we deployed OpenStack 2013. We only had the Nova network. So this is the first phase that we're going to talk about. Then Neutron appeared. So we tried to migrate to Neutron. Ricardo will talk about that. And now we are looking into SDN. So Nova network. So Nova network is a very simple component in Nova. It's already deprecated. So we started using it 2013, and we had this issue that we needed to use our network database in order to have all the information to provide an IP for the VMs. So Nova network didn't accept any plugins, so we needed to patch the code, actually build our network driver to support all of this. And basically, then is Nova network that talks with the LANDB updating all the information. This is hard because it is a patch that is important for the infrastructure. We need to maintain it, release after release. It's very hard work. Also, then Quantum appeared. It is the right moment to migrate already to Quantum, change name, Neutron. The infrastructure continues to grow until we reach a point that we need to move to Neutron.
Yep. Okay, so I'll cover, this was the introduction of how we got to requiring Neutron. As Belmiro was describing, we have some restrictions on the network at CERN. Our motivation to move to Neutron was basically that Nova network was disappearing. It's not like we would gain a lot of functionality because we still had these restrictions on the network, but we wanted to keep with the pace of the OpenStack developments. So we had to keep the restrictions on the network segmentation, the late IP allocation that is described here, things like this. So as in summary, we decided to take Neutron and just use a Linux bridge, still keep the flat provider network that we already have. But we do gain a bit in terms, when we started using it, we developed this as an ML2 plugin that would add these restrictions and expose these restrictions we had. So we wrote this as a mechanism driver and 2 Neutron extensions. As we were doing this, Neutron also released the possibility to have out of 3 plugins, which is a big plus. So we could just have our own plugin living in a different repository and just use the upstream packages. So this was very good for our operations. Also, around the same time, there was some design work going on to introduce Neutron segments as a user-facing API. Neutron segments already existed internally, but they were not exposed to the users. So what we implemented is very similar to what ended up in Neutron segments, and we participated in the design sessions. So basically, layer 2 segments, and it looks very similar to what is there now. So one possibility would be that we also migrate to using segments. But for now, we still use this plugin. Belmiro mentioned that our infrastructure is partitioned into cells. This helped us a lot because it meant that we could gradually deploy Neutron and gain confidence with our deployment. And we'll see that this played a big role in our work. It did mean that we have more split pieces. So before we had one database, which was Nova, where we kept also the network information. And suddenly we kind of start splitting the network information and the instances information, which gives the possibility for inconsistencies. In addition, we have this LANDB, which is one more database that can go inconsistent with the others. So once we deployed, one of the things we had to do is to develop a consistency check tool that basically checks all of the databases and reports on failures. We never got to actually fix them dynamically, but we get reports so that we can then evaluate if it really corresponds to actual problems. So the flow is that the Nova requests will be done. They are scheduled to compute nodes, and only when the compute node is selected, then the compute agent will talk to Neutron to allocate the port and then return immediately. And then it's up to Neutron through the plugin to update the network database. So you can see that as they are diverse paths, there's some possibility that one or the other fail in the meantime. So this is actually open code. I don't know how useful it is for other deployments, as it's very CERN specific, but the code is there if you want to have a look. Our 2 extensions, one is called Subnet Cluster. So it does the mapping between the primary and the secondary IP services. So it's just to have a relationship between these aggregations of different segments. So if you do a list, you will see that each cluster can have one or many subnets. A secondary IP service is a subnet in Neutron, and a primary corresponds to a cluster. So this is how it looks. We just integrated into Neutron. It has a really nice, it's very extensible, and in this respect is really good. The second one is the host restrictions, which is to answer which subnets can I use for this hypervisor. So when the VM is scheduled, gets allocated to a compute node, we need to know where can we create the port. So we develop an extension for this. We do give extra information. In this case, it's only one subnet, but if there are many, we give information about the usage of the subnets so that Nova can, that we can decide where to distribute the IPs if we have multiple ones. Now, the big challenge was to scale Neutron in our cloud. With cells, we already had the infrastructure partitioned as in a way that would be scalable. So each cell has its own control plane, so its own RabbitMQ. So it's very easy. It's partitioned by nature. This doesn't exist in Neutron. So it meant that we actually tried to scale one single control plane. And actually, until we got to something like 1,000 nodes in Neutron, things were kind of okay-ish. We had occasional problems, but it wasn't dramatic. We started using, for Rabbit, we were using 3 virtual machines. This was working at the start, default configurations for most of the things. We didn't see any major issues. Then we started seeing a couple of issues. We increased the number of nodes, and things were kind of working. Then when we got to around 1,000 nodes, things went pretty bad. So cluster started crashing often. Not only it would crash, but it would constantly crash. It was very hard to recover. Mostly because of memory usage. So if anyone experienced with Rabbit knows the issues with the statistics collection. So the first step is just to reduce the interval for this collection. This helps a lot. The other one is that the agents, the default configurations are pretty aggressive. When things go wrong, they constantly try to reconnect pretty violently, which just does a DOS on Rabbit constantly. So this was preventing us from recovering easily. When we fixed that, we had very often that when the Rabbit cluster would go down and we would recover it, the queues would be there, but they wouldn't be able, the agents and the Neutron servers wouldn't be able to talk to each other. So this was a known issue in Oslo, but we didn't know about it. So one of the fixes we had is that restarting the Neutron servers would often recover this. Again, we scaling up the Rabbit nodes with larger VMs, as I mentioned, also helped. So this was the state of around 1,200 nodes. We thought this was okay. Then not much later, it wasn't. So we started having a lot of queued messages constantly accumulating. We would see it growing until one moment where it just collapses. And this is the moment that we decided to really invest in understanding the internals of the 2 components. I describe here a bit the conclusion that we came to. The yellow ones are the ones that might have helped, but we are not sure. The green ones are the ones that we know have helped. So from the Neutron server, mostly the configuration of the RPC stack. So increasing thread pool sizes, connection pools. The response timeout is probably a very important one, especially when we have spikes on the number of messages. So this is a clear one to increase these timeouts. There's not a lot of, at least in our deployment, because we don't rely on these messages for a lot of things. Increasing this timeout doesn't have a big impact. And of course, the RPC workers, we then learned that actually this value is not necessarily the one that is handling the Rabbit messages. There's another parameter that controls this. I'll have it in the next slide. So it might have worked. Now, the ones that definitely work were the Rabbit configurations. So the TCP backlog is the number one, because it takes a lot of the load from the Rabbit servers and into the TCP stack. So this allows the queues to be much more efficient. TCP listen options keep alive, things like this. The memory high watermark, it really depends on how big your servers are, but we are keeping it at 0.8 and gives us enough margin to react when things go wrong. Then U limits definitely increased. One thing that we are still not completely sure about which mode we should use is the partition handling. So for Neutron, we are currently running with AutoHeal, and it sometimes works. Like I would say most of the times it works, but not always. So for other control planes in our cloud, we are actually running with post-minority. So, but we wanted to experiment with AutoHeal to see if this would be a solution. So that's what we are running in Neutron. So that was 2,000 nodes. Then we get to 2,400 nodes. So it crashes much less, but it still happens. Sometimes the queued messages go a bit too high, and it eventually crashes. So here, one big detail is that we run Rabbit in virtual machines. I know that many large deployments are running in physical machines, so this is a detail that I would like to put here. And this is also the moment that we gave up basically on scaling Neutron as we would like to run it. And because we have this limited usage of Neutron because of our network restrictions, the agents are not that important for us. So we just change the configuration so that they report their state much less, a lot less, and also the server to accept that. Basically, this reduced dramatically the number of messages in the control between the control plane and the Neutron agents, and basically this solved it. But it's not ideal if you're using other functionalities from Neutron, but for us this works. We still have this value that allows us to detect issues with the hypervisors in most cases in advance to actually the user seeing the problems. And we have all the monitoring in place so that we react. So whenever an agent is reported as down, we will make sure that things recover properly. So I put here on the bottom two more things that we looked at, but it's a bit unclear what we could do with them. So the first one is the RPC state report workers, which is this other value in the Neutron configuration in addition to the RPC workers. That should be increased if you want to scale the number of threads processing the rabbit messages. So this is the value that you should configure in Neutron, not the other one. The other one has no effect in this respect. The second one is the heartbeat timeouts directly on the rabbit cluster, which is different from the timeouts for the agents. We played with this, and it seems that it didn't help. It actually made things worse. It's unclear why. And at the time, we were kind of in a crisis situation, so we didn't have a lot of time to investigate in detail, but it didn't help. So this is the state today. So since 2,500 nodes, we've been scaling. We have already 5,000 nodes in Neutron, more or less, which is kind of halfway where we have to get to. And because we doubled from the last time we saw big issues, we are pretty confident that we'll be able to scale this all the way. So it's a stable cluster where the rabbit cluster is running with 564 gigabyte of VMs. So it's pretty significant resources, but it seems to be working. The current issues we have is network partitions. This is to be expected. Most of the times it recovers by itself, not always. So when it doesn't, it's very hard to recover manually. So we developed a procedure where we basically wipe out the thing and we start from scratch. And by trying a couple of times, we got to one that implies 10-minute downtime on Neutron. Because Neutron is only relevant for us during VM creation, this is not dramatic. But it doesn't happen that often also. I don't know how many times it happened in the last couple of months, but it doesn't keep us from sleeping at night, so it's okay. So some graphs, I don't know if you can see from there, of our monitoring. So on the left side, we see the queued messages in Rabbit, so it's pretty stable. Like we can see some spikes to 30 messages. Sometimes we have spikes to 1,000 messages, but that's okay. Even when we are recovering from a downtime, we'll see spikes to, 100,000 messages, and the thing will just recover gracefully. So that's all good. The number of messages per second, we have a couple of thousand from time to time, but most of the time is very calm. We have 90,000 Rabbit consumers, something like that, with 70,000 queues. I don't have the number here, but it's something like that. And then here is the Neutron values. So for the GET requests, it's in the order of a second, less even, so that's okay. Then we have some variation for the put requests and the post updates, but it's manageable. The main reason for this is that we run a lot of Kubernetes clusters, and the configuration of the Kubernetes cloud provider right now puts a lot of load on the metadata service that also talks to Neutron. So this is why we have a lot of requests going on, something like 60 requests stable per second. But there's really no reason to keep this. We'll eventually figure this out. The other thing is that we are not using the memcache for the tokens yet. We are just about to deploy it next week, and this will reduce a lot the load also on the servers. So it took a while, but we are at the point where it's pretty stable with a few thousand nodes in one single region. So that's pretty good. The other thing I would like to talk is the migration process. So two details. We use Puppet for the configuration of all the nodes. So we also developed a Puppet recipe to do the reconfiguration. It's very simple. There's nothing special there. Now, to actually do the migration of the hypervisors, it's a bit more tricky. We have to play with the bridge and all the tap devices on the bridge, the naming schemes and things like this. So here we had to put a lot more work. What we decided to do was to write an extension to the OpenStack client with a new command for doing a migration. So we basically do migration cell by cell, which for us means migrating the Neutron clusters, the clusters with this extension that we have. We can also do it on the basis of one hypervisor. So usually what we will do is take a cell, do the migration on a couple of hypervisors just to see that things are well set up for this one. And then we run on the full cluster. The code is available. Be aware this is very CERN specific. You can easily see from the code here like lots of hard-coded things because that's how it goes. What it generates is a long list of commands that should be run in the hypervisor in one go so that it can bring down remove all the tap devices, bring down the bridge, rename everything, recreate the bridge, put everything back in the bridge, and we're back on. So, but this has to happen in one go and without failures so that we don't have to log in to all the hypervisors. If we lose connectivity, it's pretty bad. So this is how we are doing. And we've been testing, we've run this in a few cells already. So it seems to be okay. What we did, the main purpose of doing this in a command and isolated is that we don't have to do all the migration of all the cells, like myself or Belmiro, but we can delegate to all the members in the team. So the recipe is easy enough that anyone can pick it up. So this finishes a bit the architecture that runs our cloud today. So as we mentioned, even the migration to Neutron that didn't really bring us any functionality, but we really want to start giving like the fancy stuff. So we started looking at how we could have a software-defined network. We started looking at it last year together with the networking team at CERN. The main goals is to offer IP mobility. So currently we have this segmented broadcast domain that restricts a lot what we can do when a VM has an IP. We can not really just migrate it to a hypervisor in a different broadcast domain, so it doesn't work. We do this on an ad hoc basis when we have to retire a lot of hardware from one cell. We create ad hoc tunnels between manually between the IP services, and we do the migration, and then we retire the nodes and kill the tunnels. This works, but it's not flexible, so we would like to do this automatically. Hardware repurposing is the other part. So we have multiple network domains. When a bunch of nodes are allocated, say, for the batch service, and we want to reuse it for general services, we can't easily do this because the IP allocation subnets are different. We can't offer floating IPs today, so that's also a limitation. And then we only have a flat network, so we provide them. And we can't have private networks. So with an SDN solution, we get all of this. We started evaluating a couple of products. So we tried Neutron with Open vSwitch, Open Daylight, and OVN. This evaluation wasn't at scale. We just wanted to check that functionally they were kind of similar. If we look at the main things we want to offer, like floating IPs, it's pretty clear that they all support it. Distributed routing, we have a large infrastructure, so we have to have this from the start. They all get it, although Neutron only with DVR, but it's there, so it should be okay. Tunneling protocols, at least to have some flexibility on what we can use, like Open Daylight, OVN, they all use OpenFlow, support for load balancing somehow. DPDK is something that we probably will need also. And then the debugging tools. So this is a quick summary of the evaluation we did. We actually deployed all of them to make sure that functionally this was true. So we didn't deploy them at scale, but we did go through the process of making sure that it all works. So after these 3 evaluations, we chose something different. The reason for this is because we just renewed our contracts for the hardware in the data center, and the vendor is Juniper. So we considered what can we get from it. And at the time, Contrail was also opening up with Open Contrail, and it got taken by the Linux Foundation, rebranded to Tungsten. So we took a dive on understanding a bit what can we get from it, and functionally, definitely we get it. There's a few large deployments that also gave us confidence that this would work for us. And then there's a big plus, which is what I put here, is that all the infrastructure for continuous integration and contributions looks very similar. So if you are working with OpenStack, and we do a lot with OpenStack, even contributing upstream. So we are used to Gerrit, reviews, there's Zool. They check all the patches against Okata and Queens. So it felt very familiar and positive, and also our interactions with the community were very good. It sounded like because we have the vendor, we have the knowledge in the networking team for the hardware, doing something at the OpenStack level that kind of matches what we have there is a big plus. Also because we have a need to extend the network from the VMs to the physical layer too. So a quick summary of how the architecture looks. So you have a control plane that you can have multiple replicas of everything. Then you have at the hypervisor virtualization layer, you have to run a component called the vRouter. Then you have integration with the physical devices too, and then gateways if you need access to external networks. The protocols being used are here, so there's no OpenFlow, but there's other protocols. The main ones we are looking at now is what to use for tunneling. So I think the recommended one is MPLS over UDP. We might go with VXLAN to see how it goes, but it's not sure yet. We are trying both of them, actually. Some details on how we deploy this. So the community upstream generates containers and is very active in both the deployer using Ansible and using Helm. They're not, like the Puppet modules are quite poor, so we didn't consider that after a quick look. So we decided, because we have a lot of experience with Kubernetes also now, we decided to deploy a cluster using Magnum for the control plane and just use Helm for the configuration. And this was a couple of hiccups that we fixed upstream, but this worked very well. So we got the control plane going very quickly. Also, the RPMs are not that easy to get. They are generated, but the sources for the RPMs, as far as I understand, are not easily available. So we decided to go with Helm and just container-based deployments. Then on the vRouter part, we had the same problem. The problem here is that we already have a setup for the hypervisors, which is based on a Puppet. So to run this component, we just wrap it in a Docker container, and we run the vRouter component using Docker. And the last bit is the Neutron control plane. So here there are 2 options. One is to use the monolithic plugin of Tungsten for Neutron, and the other one is the ML2. So the state of the monolithic one is production ready, it works very well. ML2 is still getting to that state. So we chose the monolithic. The main difference here is with the monolithic, Neutron becomes just an API. So the Neutron database is pretty much not used. Has the advantage of no inconsistencies between yet one more database, but you lose some of the functionality. So the extra APIs, some of the extra APIs of Neutron, you cannot use them directly. You have to use directly the Tungsten API for similar functionality directly in the Tungsten control plane. The last bit is that we do this in a separate region. Integrating this with our production Neutron proved to be a bit complicated. So we are deploying a new region, which we call the SDN region in the CERN cloud. And with that, we get to the summary to leave some time for questions. So scaling Neutron, even at a very simplistic case, was not trivial and mostly due to RabbitMQ. Right now, we have it in production with thousands of nodes and it's stable, so that's really good. We are finalizing the migration from Nova Network to Neutron. It took a while to get confident with the procedure, but we already did enough cells to be confident that we'll dedicate like a month to finalize the whole thing and we'll get it done. We evaluated different SDN solutions. We chose Tungsten and are deploying it in a new region. And we really look forward to offer a more flexible network to our users. It's something that right now we will be able to do. So hopefully in 6 months or a year, we can come back and present how it went. And I think that's it. Thank you very much. So if anyone has any question, yeah, you can walk to the mic.
Thanks for the interesting presentation. Samir from Line Japan. So we have pretty similar use case in Line. We choose to use slightly different approach after dealing with Neutron L2 domains. So I was wondering, you haven't given any technical reason for choosing Tungsten.
Right.
Is there any?
I probably not. Like the comparison we did with Contrail, it would probably be similar. It's really the moment where we were looking at it is the moment where the vendor was chosen, and the interactions with the network team, because we will have to deal a lot with the lower level networking team at CERN. It kind of felt better to also evaluate Tungsten and see if it offers the same functionality. And it does. And from that moment, it's kind of an easy choice. And also, in addition to the technical requirements, the interactions we had with the community and with the people in the Open Contrail, they were very positive. So that was also a plus. Also, sometimes Open Contrail is very big. It's not so easy to track the different components. So in here, it felt familiar. What they offer is what we need. So.
Oh, thanks. A follow-up question. Have you evaluated the performance impact on using other SDN solutions, and Tungsten as well?
No, we didn't get to any kind of scale yet to provide the results. So we are basically at the functionality part. Yeah.
Okay. And final question: the Neutron scaling issues. So I guess you were using the same Neutron control plane for these cells as well as regions.
Yeah. So maybe you can answer this, or I can answer.
No. So we have the control plane for each cell, and then we have a separated control plane for Neutron. And all of them use different RabbitMQ clusters.
So the scale issue was like one cell?
So Neutron is a central service that is used by all cells. So all the compute nodes, all the agents running the compute nodes will talk with the central service that is Neutron.
Right. So one possibility, maybe that's where you're getting at, is that we could have split the cloud into multiple regions and solved the problem. We could have done that, but like we already offered only one region. Splitting it after it's there would have implications. So
it's architecture choice. Our choice is not to have regions, or at least at the beginning. It was to have multiple cells and have only one endpoint.
Thank you very much, gentlemen.
yeah.
Did your network team offers you the SDN or only a base layer network and you produce your SDN by yourself?
That's it, yeah. So there's some challenges there regarding the level of integration we have to have with the lower level layer, especially because there's a big split in the CERN network between the general network, which we use for virtual machines in OpenStack, and the technical network, which is used by the detectors and accelerators. There's a real split. We also have restrictions on the availability of services. So if there's an issue with the general network, the technical network has to have the capability of cutting it and still run. So that's where also we want to evaluate SDN solutions where we can do the bridge, being able to cut the general network, but still keep running the technical part. Yeah.
Thank you.
Yeah, welcome. Okay, thank you very much.
Thank you.